Hi, everyone. I am Anca Dragan. I'm a professor at UC Berkeley, where I run the Interact group. And I wanted to share a little bit today about some recent work and what language can teach us about the reward function that an assistive agent should be optimizing. And so to put this in context, I'm a roboticist by training. I specialize in sort of human AI interaction, human AI collaboration, and I've avoided natural language interaction like the plague so far. But lately, I've been feeling that I really won't be able to truly understand human AI interaction without actually understanding something about how human and machines can interact through language as a communication modality as well. So diving right in, I want you to imagine an interaction with an assistant where you as the user tell the assistant, okay, I want to fly to JFK on a particular date. And the agent shows you a list of available flights and you look at them and you trade off things like their price, their duration, how long the layover is. And you might have a preference even for one of the carriers here. And you put all of that together and you make a decision and you tell the agent, look, you want to go with the first flight. And so now the assistant can go and book that first flight for you. But what interested me about this type of setup is I claim that the interaction that you just had should not only help the agent know what to do now in the moment, go and book the flight, but should also help the agent in the future as well. Right? When in a week you're booking your flights to Chicago, I want that agent to have a better idea of what flights you might actually want. And eventually, I want that agent to be able to start acting a bit like a proxy for you where I can autonomously take decisions that you would take when faced with those situations so that you don't have to spend your time on every single little thing. So the question becomes, what is it about this interaction that we just talked about that can help the agent actually generalize into the future and better help you in the future? And clearly, there's a lot more going on here than what we typically think of in following instructions. Because that would be the main paradigm that, at least for me, comes to mind when I think about, okay, I need to make an assistant that responds to natural language commands. Clearly, instruction following is not enough. So as a roboticist, I'm particularly used to reading instruction following as my way into natural language. And roughly speaking, a user might want to say something like, go 3 steps forward, then turn towards the door. And there's a lot of work on mapping that sequence of actions that sequence, mapping that utterance into a sequence of actions for the robot to take. But if you think about the role of language in communicating to an agent, yes, sometimes we're helping the agent do a task like this, right? By spelling out exactly step by step what the agent should do. But this is meant in a sense for these incapable agents who, for instance, might not be familiar with exactly the environment and might need help to, for example, figure out exactly how many steps, 3, it needs to take before it can find the door. So you only really talk like this to an agent that sort of desperately needs help from you in order to achieve its goal. It wouldn't be able to achieve its goal on its own or not as efficiently. And that's, of course, helpful. But other times we might give an agent a goal directly, like go to the kitchen, or even a higher level thing, like get me a drink from the fridge. And so you would do this, right? You would rather do this. You're more likely to do this with more capable agents that are able to actually execute on a goal on their own without sort of your step-by-step guidance. So that's another way that you might instruct a robot. And then when we give more detail, like if I were to say, hey, don't step on the rug, that might not really be anymore about the agent sort of not knowing the environment or needing my help to reach the goal. It's much more about imparting sort of my preferences onto the agent, like keeping my pristine white carpet that I just purchased clean, right? So I don't want a robot to step over it. And so as we get agents that are more and more capable at sort of executing on goals and preferences, language instruction becomes, I think, much more about communicating about what these goals are, about what these preferences are, which we can formalize as the agent's reward function that we'd like the agent to go ahead and optimize. And even though my lab has done, it's a bunch of work on learning reward functions. We've done that from all sorts of inputs like demonstrations or physical corrections or even the state of the world. But recently, I've become really interested in how language too communicates about rewards and not just about the step-by-step actions that the robot needs to take. So coming back to the flight booking example, like much like I might have this preference about how a robot does stuff in my home, about my rug and so on. Here too, in this example, the user has preferences about flights, right? About what matters to them when they take a flight. So for instance, they like to fly JetBlue, they really hate Delta, they don't like expensive flights, but what they really, really hate is long layovers, right? And so they put all that together, and that's why they like the first flight the best, and that's why they tell the agent book the first flight. And what we'd like is for the agent to not only take that and book the flight, but also to learn something about the user's flight preferences, right? They're shown in the top left, that then the agent could use in future flights, in future tasks when it needs to book a flight for the user. So language should teach the agent about the user's preferences more generally, right, than wanting flight one out of these 1, 2, 3 options. But the question is, of course, the how. How do you infer rewards? How do you infer preferences from language like that? And my first instinct here was to do what I've learned in the reward learning tasks that I've looked at before. So traditional reward learning is based on demonstrated actions. And this is really what we have here, right? So in demonstrated actions, you show a robot what to do, sort of step by step, and then you enable the robot to figure out what reward function is consistent with the demonstration that it saw. So here too, the user chose this flight as opposed to the other two, and that's a demonstrated action, right? So the booking of this flight is in a sense a demonstrated action. And the robot now knows a bunch of things. It knows that approximately the reward function assigns higher reward to this flight than to the other two. That's what it means for this flight to be preferred. And from that, it can figure out sort of what reward functions are consistent with that. So the user might like short layovers. They might love JetBlue. That could also explain why they chose this flight. But of course, another explanation kind of consistent with this choice is that the person is really just maximizing price. That's also would explain why they chose the first flight. And so there's a lot of ambiguity still. And as we were thinking about this problem, we remembered that we're dealing with language. And what's different from language compared to the typical sources of human input that I deal with is that, like, actions, right? With language, it's purely communication. Like usually I look at human behavior and interpret it as implicitly communicating about the reward, but language is communication. So maybe it actually directly communicates about the reward. Who would have thought? So what does that mean? Well, if you think about it, the user doesn't make a choice for a flight by kind of clicking a button, right? They're using language to describe that choice. So they actually tell the agent what flight they want. And what they said here is, in this example, is I'd like the JetBlue flight. They could have said other things that would have identified this flight as the correct one. They could have said, book me the expensive flight, but they didn't. So that's a choice too, the choice of how to refer to the action that you want. And that's what language brings us on top of the instructed action. And so the key idea in this work was that language communicates about the reward in sort of 2 ways. The actions themselves that the language refers to communicate about the reward. Yes. But the way that people refer to the desired actions also leaks a lot of information about what people care about. And so from a language perspective, another way to say this is that language that kind of takes a long horizon into account, takes the sequential nature of the task into account. So an utterance is there to optimize, not just to communicate what to do now, but also to inform about what will help and how to act in the future. So it's this like long horizon a sort of planning aspect or decision-making aspect that we have to account for when we think about language in the moment. And that might remind you of a reference game, right? So I'm talking a lot about, well, how I choose to refer to and what it identifies. In a reference game, like if I typically, I would say, I like the man with the hat, right? In a reference game, would think about, well, what does that mean? Which one do I mean? In this case, what I'm talking about is the listener not only identifying which person the speaker is referring to, but also learning something about what the speaker likes that will help the agent identify in a future reference game, like in a future situation with different options where the choices are different, what the speaker is likely going to refer to. And so this is like a reference game that repeats with new options over time. And in every situation that shows up, the answer is kind of guided by the same underlying structure, by some latent state, some speaker preferences that sort of dictate what the speaker will refer to. We'll parameterize these preferences by theta for the rest of the stock. So I want you to remember theta as the reward parameters. And so that can encode, for instance, the trade-offs that people want to make, how much they weigh one important feature of a flight versus another. And the game that we're playing is to listen to the utterance and not only identify the action, which flight to book, but also update our estimate of theta. And so we can put this in a pragmatics model. We have a pragmatic listener, our agent, that tries to infer what theta is, what the reward parameters are, by hearing an utterance U and taking the context of that utterance into account. So in the flight task, it was the set of choices available in general. We're going to think about this as a Markov decision process. This is the context. This is the MDP in which the agent needs to act, and the trajectories in that MDP correspond to different choices. And now the listener infers data by modeling how the speaker might be generating utterances based on data in context. So the probability that the speaker says that utterance U, given that data and given the MDP M. And there's, of course, a prior, which you can get from something like meta learning. And importantly, your posterior here becomes your prior for the next task instance that you see, where you get to learn more and more and more from each utterance. So roughly, that's what we'd like to do. And now there's a question of, well, what's a speaker model here? So how do you model the speaker's utterance generation? Well, there's a few options. Reference RSA will link the utterance to the action. And it will say that the speaker will choose an utterance that elicits the right belief in a naive listener. So that's reference RSA, but that belief is importantly over actions, not over theta, right? Not over rewards or preferences. The only relevant world state belief is about actions. What action is the speaker referring to? Then there's techniques based on inverse reinforcement learning, which are sort of more my comfort zone, which is basically model the speaker as choosing utterances that refer to the desired actions, and then acknowledge that in turn, these desired actions give information about the reward. In that way I was describing earlier, what rewards are consistent with this being the preferred action. So you think of actions as choices, and you think of higher reward being associated with the actions that are actually chosen, the ones that are referred to. And then you ask what rewards are consistent with that. But even with this, utterances don't really say anything about the reward or preference beyond the actions that they identify, the actions that they refer to. So language is only there to pick an action, and the way you get information about the reward is really only through which action gets picked. And so that doesn't really allow for that second modality that we talked about, where the fact that I said just blue and not expensive should actually give me some information on top of that. Here in this base net, utterances are independent, conditionally independent of rewards when conditioning on the actions. And so in our work, we wanted to bring in that information that leaks kind of directly from the reward into language, into sort of the choice of how to refer to the reward. And we actually kind of take a really simple approach to that, which is to say that given theta, the action, in a sense, trades off between referring, the utterance trades off between referring to the action and referring to the reward. Okay, so we're modeling the speaker sort of caring about both of these objectives. I need to convey the action, that's important, but I also, for long-term purposes, need to convey the reward. And so speakers choose utterances that elicit the right actions in a listener, but that also faithfully describe the reward. And digging into this action part, the first term, as the speaker, you would see sort of the reward data, and you would choose which flight is approximately optimal according to that data. So which you want to refer to. And then you would choose an utterance that appropriately refers to that flight. So you can write that, you can write the probability of U up top here by marginalizing over actions and looking at how high the reward of that action is under theta relative to the other. So that's the choose a flight that's good with respect to the reward part. But then you would also look at how well the utterance U identifies the action for a base listener. So that's U given the action side. So then the speaker also accounts for how well the utterance actually refers to the reward. And so here we actually use a base speaker model for this. We didn't get a performance boost out of a pragmatic one, but in general, that's a possibility as well. And so we take these and we put them together with a little bit of a cop-out, which is the alpha trade-off. And this is really one way to capture the spectrum that speakers might lie on. On the one end of the spectrum, you have speakers that only care about identifying the action for the listener. And that's so that the listener can, you don't care about the listener doing well in the future. And so you might say something like flight number 1, because that does a great job at identifying the first flight. Of course, it doesn't really give you any additional information about the reward beyond the fact that you won the first flight. At the other end of the spectrum, you really want to refer to the reward, and that's what you care about. You really care less about the current action that's being taken. So you have a very kind of long horizon view, and you could, spell out some careful description of everything that you care about and how much you care about it. And so in between, there's other points, like one user actually said, I like JetBlue, but not too expensive and definitely not too many stops. So that's giving a little bit of extra information, a little bit of extra context there for their choice. And in the example that we saw, our starting example was you just say the JetBlue flight, but you said the JetBlue flight, not flight number 1. And the fact that you could have said the expensive one should still give you some information as the listener. Okay, so speakers choose utterances that elicit the right actions in a listener and faithfully describe the reward. And then in turn, listeners infer rewards that would make a speaker pick out the actions they're describing the way that they're describing it. Okay, so to test this out, we did our own data set collection and a task that we call flight prep. We paired humans together, and one human was in the role of the user and the other one was in the role of the assistants. And we did our best to sort of incept a reward function into the user by giving them instructions on what kind of character to impersonate, so sort of what their preferences are, and make them care about the task. And then they played multiple rounds, and each with sort of a different choice set, different options to choose from. And the person playing the agent was rewarded for choosing correctly the flight, but also they were able to ask for another utterance, and that would be a little bit of a penalty. And then there was a much higher penalty for choosing incorrectly. And they were actually penalized or rewarded together as a team. And so that made the user also try to communicate things about future rounds. Here, by the way, some of the data that this elicits. So you see kind of a mix of reward descriptive and trajectory descriptive language or action descriptive language. There's also, there's partial descriptions, and even for like full descriptions where the person would try to say their preferences in natural language, they would still be sort of trade-off uncertainty of just exactly how much is this word versus that. Is it 5-to-1? Is it 6-to-1? Is it 5.8 to 1? What's the sort of the right trade-off? What is the right ratio there? So it's hard to kind of directly infer the reward function fully from an utterance, right? But you put them together over time and you get closer and closer and closer. So the way we evaluated this was we looked at the behavior that you get out of optimizing the infer reward in sort of test and held out situations. We also looked at the error of the reward directly, and those results are sort of similar to the held out accuracy metrics. So I'll mainly focus on that one. And so what we're going to see here is, compared to random chance, what sort of our method does on held out accuracy versus baselines. And on the right-hand side, you also see performance of oracles that out of the 8 features that were important to the users, these oracles get to know perfectly the values for 1, 2, and 3 of those features. And so on the x-axis, we'll have action only, reward only, and then our approach, which is all about combining the action reference information with the reward reference, direct reward reference information. So it turns out if you do action only, that does the worst. And it's actually better to do reward only on average. That was hurtful for me, saddening for me at first, because the action only approach is in a sense sort of the thing that I would go to as a roboticist. I would think of, oh, you're identifying an action, therefore you're making a choice, therefore that tells me something about what you want. But actually just learning a model that talks directly about rewards ended up performing better as a speaker model for our listener. And then, of course, sort of as expected, if you actually model people as doing a kind of a combo of action and reward, and this was with an alpha that we set, we didn't actually adjust it yet to the individual users. But if you find sort of, I think we used alpha 0.5, if you set alpha to 0.5, this is sort of what you get. You get something that's slightly more accurate by actually putting together the information from the choice of the action and the choice of how to refer to that action. And then if you look as a function of the observed number of utterances, right? So the amount of information you actually get about the user, you end up with everything doing better with more information. That's not surprising. And the gap is big in the beginning compared to the action only. So again, that's, sort of the more inverse reinforcement learning type of approach. And then the gap shrinks with a lot of utterances, where as you observe the person making multiple choices, you actually are able to learn more and more and more and more. But at the beginning, tapping into the really solidly language aspect of this seems to be the most powerful. And so again, the key idea of this work is that language communicates about the reward in 2 ways. Yes, there's the actions themselves that the language refers to, their choices, and so they communicate about preferences. But the way people refer to those desired actions ends up leaking a lot of useful information about what people care about. And again, I think this points to, from a language perspective, to this view of thinking about language in the context of sequential problems, where what the speaker currently says has to do not just with the now, but what will happen in the future as well. And so instead of focusing on actions, focusing on generalizable information and reward functions. Okay, so in terms of limitations here and future work, we just set alpha to 0.5. Clearly modeling alpha, being able to infer alpha for different individuals might actually be getting us the best of both worlds here. We use the reward posterior in a kind of a very naive way, but you could use it for active learning, right? Probing more at the person. You could use it for risk-averse planning, sort of hedging your bets and deciding between those options. And also, we used a really simple reward representation, right? It was weights on known features, and the real user preferences are much more complex. They depend on many features that we don't even know. And so looking at deep representations of reward functions could be really useful here. But overall, I'd say the takeaways are, we should be thinking about language as informing us about people's goals and preferences, and thus an assistive agent's goals and preferences. So the reward function that an assistant should optimize. And how do you do that? You look at what people say they want to do and how they say what they want to do. And then in general, I think we're excited to start really digging into these long-term interactions that we think introduce new modeling challenges. And we've taken, I think, a first step with this sort of alpha trade-off between a long horizon and a short horizon. But there's, I think, a lot more nuance that we need to look at in the context of language as a way to sort of interact with the sort of the physical world or a virtual world and build up an understanding of the person you're interacting with over time. And so with that, I'd like to thank you, and really to thank Jesse, who is the main author on this work. So take care, everybody.